I'd like to invite Karsten Flensberg to moderate the discussion and maybe give his own point of view.
Okay, so thank you. I'm Karsten Flensberg from Copenhagen. So I was asked to stimulate a discussion about this session here. We just had two very interesting talks, and I will try to steer us towards what are we going to do next. So there have been, let me find the laser pointer. There have been, many theory proposals about how to generate topological states, both intrinsic and in engineered systems. And in the previous session, we heard mostly about intrinsic systems, maybe. But the engineered systems, there are several. Roman talked about the semi-super, the topological insulators, the quantum Hall systems, which we will hear about tomorrow, atomic chains, and gold and europium systems. But in all these cases, the usual signature we are looking for is zero modes, and we spend a lot of time discussing zero bias conductance peaks. And they only, as we have talked about, give partial information. And I would claim that even in principle, DC transport cannot exclude other explanations like Andreev states or quasi-Majoranas. So the next step will be to do some kind of correlated appearance of Majorana zero modes and non-local conductance experiments that Roman discussed, which is still DC, and therefore in principle does not touch on the deeper physics, namely the non-local information stored in the ground state. But still, it's a step forward. So my first question to you would be, how do we move on from keep discussing the origin of zero bias peaks? Or are we even there? All these nice theory papers that come out all the time about how to mitigate errors and so on, are they really relevant before we know if Majorana modes exist and in their interesting non-local properties? So if I should answer this question, I think that one of the first experiments would be this, what I call the full interferometer. Even though it's still DC, it's really hard to think of a way that this could happen without an information stored in the ground state of a wire if it's long enough. So I think that's an important experiment to do. And another direction to go is to go more time dependent, and in this case noise. If we had a bunch of Majoranas and current running in and out of these three leads, then look at cross correlation noise will tell us something about, is this true Majorana modes, is it in Andreev bound states, and this would reveal itself in the noise signatures. But this is just two of our own ideas, and so my question number two to you is, what would be the best, and maybe some time domain, like what we heard in the last talk here, experiment that would probe the true non-local behavior in the ground state and distinguish it from ABS. I don't know if there's some inputs already now, or I should go on.
So far, there's no inputs in the chat.
Okay, so let me take question number 3, and then we can 3 and 4, and then we can take them one by one. So this third question here: why are we still, after roughly 10 years, basically not moved anywhere in terms of the more interesting physics? And maybe it's for a fundamental reason that it doesn't exist, or it's for material issues. And we can take them one by one. let's take the semi-super systems that Roman talked about, and I have one question for him. You know, what is the spin-orbit coupling? Is it really what we think it is? Is it a Rashba type that it needs to be? And how is it actually simulated in the simulations that were shown? And okay, or is it too much disorder, which was discussed? So if we got rid of all the disorder, would we be home free? And for the TIs, we can discuss, is the bulk density of states small enough to actually see braiding and non-local physics, or is it killed by poisoning because of the residual density of states in the bulk? For the fractional quantum Hall systems, maybe this is the future, or we haven't heard about this, so I'll just skip it. For the atomic change, I think the big question is, can we ever go beyond the STM and do something which is not transport? So we can take them one by one. So an alternative approach, which I like, is to, so we heard about making chains, sort of an artificial Kitaev model, but why not use artificial atoms in that artificial chain? You're making chain of atomic-like orbitals in quantum dots, like in this picture from this paper, or even just two dots can do it. Something we call the poor Majorana, and then increasing the number of dots going toward the exponentially protected regime. So this would be an area where we actually really concretely understand the details of the physics. We don't have to rely on material properties that we don't understand, like the spin-orbit coupling, for example. Okay, so these were my 4 questions for you. 1, how do we move on from discussing zero bias peaks all the time? What's the most important next experiment? Let's take that one first.
Well, what about connecting to transmons and measuring the absorption of light?
Yeah. Why would that give new information?
It's give you detailed information about the spectrum, not necessarily local.
Doesn't it rely on overlapping Majoranas and
So there is one simple thing that extends what was just said. Again, I'm not sure you know that it's so profound, but if you look at the transitions between the Majorana state and the next Andreev state, the trivial Andreev state, which should happen in a longer junction, then it depends on the phase applied, the phase difference applied, right? Flux phase difference applied. But then, if you may go through the transition where the Majoranas intersect, right? So the odd state goes down, even state goes up. So in principle, there should be a spectral signature in the transition frequency as a function of the phase bias on the junction. So that was Siri's suggestion some time ago. It's a difficult experiment, though.
and this is something specific for Majoranas?
theoretically, yes, because you see, these two Majoranas have different number parity, so they're not
coupled.
They're not coupled, right? So the frequency versus phase should have theoretically a very sharp kink, because you have two states that don't hybridize. But I think that it's difficult to experimentally to distinguish a kink from a rounded kink. So that I think is a. But I don't think that it was ever developed into experimental enterprise.
So maybe that connects to question number 3, because maybe this experiment wasn't done, but many of these experiments have been done and have not been successful. I think that's fair to say by now. And so is it because it doesn't exist, this physics we are looking for, or are we still searching the material issues that we don't understand, or do we just need to refine the materials? So to you, Roman, do you think you have all the ingredients in your modeling that you need?
Yeah, so I raised my hand. I didn't know whether I,
Oh, okay, I didn't see that.
Okay to interrupt. Just from my perspective, maybe a couple of things that I want to highlight. That, look, the model is non-interacting model. It's a mean field model, weakly interacting, mean field approximation for superconductor, otherwise non-interacting. That's the simplest model that one can, think of. So if you're not successful at this level, I think correlation physics and, including interactions will make things even more complicated. So therefore, to me, the first class of experiments is just, these are experiments with basically at this weakly interacting level. And to your question about spin-orbit coupling versus these other physics, we do see spin-orbit effect in non-interacting systems routinely. They appear in weak localization measurements. They appear in level anticrossing of Andreas states. They appear in many, I think, experiments. Weak localization, that's a standard measurement that, one can, clearly rely on this textbook measurement to extract spin-orbit coupling. So we definitely see that.
I'm not doubting that there's spin-orbit, but is it of the right type? Is it this simple ASPA that's put into the modeling, or is it just some disordered spin-orbit coupling?
Well, of course, it depends on the story is more complicated. It depends on crystal, right? Because there might be Dresselhaus, there might be Rashba, but I think if there is electric field at the interface, then we know that the electric field at the interface and there is inversion symmetry leads to Rashba spin-orbit coupling. So I don't know whether this is a question that there is no spin-orbit coupling. I think to me it's not a question. It's a fact.
No, so you're saying it's allowed by symmetry. It doesn't mean it's there.
Yeah. So the question is, what's the magnitude of that that effect, right? And again, you can compare with weak localization measurements to see and check the magnitude. In simulations, we also use standard procedure. We go to KITP models and use electric field coupled to holes and generate spin-orbit coupling. So usually you can do it either one way or compared to experimental value, and then it's within a few factors from each other. So if you're asking a question about factor of 2, then okay, there are error bars on these measurements. But I don't think it's zero, if that's what you were alluding. To me, the main problem is actually disorder in the systems. If you look at band structure and scattering and so on, requirements to realize topological phases, at least in the semiconductor nanowire with aluminum, are quite stringent. So disorder physics is the main culprit, in my opinion, at least at that level.
Did you have yeah,
can I
sorry.
ask?
Yeah, you want?
Roman, is it disorder per se or the combination of disorder and large magnetic field?
Well, yeah. So when you are driving the system into class D, right? So disorder becomes more has more profound effect on the system. So certainly that's the case. But overall, I would say it is disorder physics, and it's kind of the main competitor with Majorana physics, with topological physics.
So you're saying it's the lack of Anderson theorem in class D, basically, that can kill you?
Well, it's more than that. It's propensity for states to form these basically Majorana pairs when you have potential fluctuations, and these pairs of Majoranas that are created at domain balls, they just give to the divergent density of states when the disorder exceeds a certain critical level. It's actually much worse than what would you get from some kind of bulk calculation and take into account time reversal symmetry. It's dominated by these rare events, basically Griffith physics and so on. But going to cleaner materials, higher TC superconductors is something that I think is important for this field, at least for semiconductor nanowires.
Okay. Yeah. So it's just keep working on it. Any more comments to this?
There is a question in the chat.
Okay, I don't see the chat for some reason.
Okay, so Igor Brino, maybe you can just speak up.
Yes, I had a question to Roman. What determines the critical level of disorder that you mentioned?
Well, generally, this is called localization delocalization transition is determined by the localization lengths in these quasi one-dimensional structures, and localization lengths, when it becomes shorter than topological coherence lengths, that sort of marks the transition to the disordered phase. So we want to have localization lengths that is much longer than topological coherence lengths.
Can you pick a material with a very small topological coherence length?
Well, that's the higher TC superconductor comment that I just made. If you have nominally higher TC superconductor, that means potentially one can induce larger induced gap, or and therefore shorter coherence lengths. But it's not just that. There's also velocity. So I mean, the formulas are pretty clear, and they're pretty simple actually.
And there's another comment in the chat from Max Gay.
Yes, hi. I wanted to ask if we wanted to be sure that we have the right spin-orbit coupling, is there an experiment that we can do that we can distinguish Rashba spin-orbit coupling from other spin-orbit coupling like Dresselhaus or so on?
Yes, there's those, but not with the superconductor on, I would say. I mean, you can look for the helical gap in the clean wire, but once the superconductor is on it, you cannot, in my understanding. Is that right?
Well, I don't know whether I would say I cannot, but I don't know
Okay, it's much more difficult. No,
yeah,
it's much more difficult.
it's difficult.
Then there is one thing that depending on the crystal structure of your semiconductor, if it's SiC blendy or ursite, then one effect can be important or not. You can be in a crystal where you don't have really Dresselhaus. Basically, I think what Roman said before, that the main source of spin-orbit coupling here comes from breaking inversion symmetry with the electric field. So if there are other remanent spin-orbit couplings, the one that is going to dominate, I would say, is the one that is produced by the electric field, which is pretty large at the boundaries between the superconductor and the semiconductor. No? And you can also increase it with the back gates.
So, yeah, so is there a way to measure that? I suppose is Max's question.
Also in the normal state, if you can verify the theoretical idea that you really have this rush-orbit coupling.
Well, one signature of spin-orbit coupling is that, that states at small magnetic fields, they do not. I mean, if you find states at low momentum, they do not disperse, linearly with magnetic field as you would expect when you have, a state and SU2 symmetry, right? Then they first start out flat and then start to, at some critical value, they start to disperse and become linear with magnetic field. So this crossover indicates that there is some spin-orbit coupling in the system, I would say. And that is in the system of superconductor. But maybe that's very weak evidence for spin-orbit coupling. Not rigorous enough for Karsten to say, okay, I understand that this is really Rashba versus something else.
Okay, I see. Thanks.
I mean, if you consider normal state transport without superconductor, then one could nail it again. There are many experiments where you can do anisotropy in the field and depending on different orientations, figure out what's the dependence of decontrolization signal and so on. There are also some experiments in quantum Hall effect regime where one can see spin orbit in the spectrum. So these things in kind of materials without superconductor are easier to observe, but with superconductor, that's challenging. Indeed.
I see. Thanks.
Okay. Anyone would like to have an opinion about my fourth question here? Do you think it would be useful to try to build artificial chains of the bigger systems that we understood and could control better? Or is it just a route?
So how is it different from chains of magnetic impurities on a superconductor?
Well, I suppose in philosophy, it's not that different.
It's the same, right? So,
yeah, but it would be more controllable. So you could easily, try the braiding type experiments, which you cannot do on surfaces with atoms that easy.
Theoretically, controllable, I agree.
You can also tune the system, right? That's the point. Yeah,
so you can easily access it, and it's more tunable. Yeah, that was.
But to kind of Leonid's point, what is the level of control that we have in these systems, and what is the required level of control that we need in these artificial atoms chains. It's a question of energy scales, so in order to answer this question, we need to first define, okay, what's the level of control we need in order to see the effect, and then maybe compare whether we can achieve it experimentally. I mean, in principle, with atoms, if you really control position of atoms, really to angstrom precision, then yes, one can build a chain. But do we have this capability? And similarly with quantum dot-based proposals, for example.
Yeah, so again, sorry for the assault, but basically it seems to me that if you take there are proximatized wires, right? So basically what you're telling that just take a proximatized wire and remove superconductor every so often and put more gates in the system. And it seems to, again, it's a question for experimentalists, but it seems to me that it's an even more complicated contraption than just a wire, proximatized wire. It's my 2 cents.
So you're working your way backwards, you're saying?
I don't know what is the what is the direction forward. So
backward is bad, forward is good. Okay, Chairman.
Yeah, maybe I can comment.
Stefan?
Yeah. On the earlier point, basically, whether this is a fundamental materials or fabrication problem. As far as I've heard recently, for example, when what is it called again? PsiQuantum, who do silicon-based quantum computing, or want to do it anyway, they now partnered up with like big fab top semiconductor manufacturers to do their fab, because they're basically saying, okay, anything you can do in a university lab is not good enough. So is there any chance to do that ever with Majorana devices, with indium arsenide and superconductors on? To go, it would be probably very expensive, but also I think there's not really that level of expertise, industry expertise in these materials, I guess.
I'm not sure who's that the question for, but are you asking whether one should go silicon way or?
No, whether one can actually do industry level fab on these materials, or whether one can find alternative materials that allow for an industry level fab. Is it worth going and trying hard to get better fab, given the current status of experiments? Maybe for experimentalists.
I don't know who is here, but who can answer that question. But I think people are trying really hard, also high quality labs.
Right, but is there any effort on industry level fab, basically, which is very high level clean room, non-university? I mean, maybe that's a question for Roman and friends as well. Whether that's something that actually a company like Microsoft is interested to invest in. Whether we first have to get somewhere more convincing with Majoranas to actually trigger that investment. I don't know, maybe it's a difficult question to answer. I guess the benefit of these silicon platforms is that they have all this expertise already there.
Yeah, I don't know who can answer that, but you're right. Maybe it could be a possibility.
Okay. Is there any more discussion, or should we close the session? I don't see any more in the chat, I guess. So, okay. Karsten, do you want to say something To close,
No, I don't know what else to say other than no.
okay, so thank you for moderating the discussion. It's nice to have other participants talk too, and thank you to all of the speakers of the day. I think we've had a quite stimulating meeting today, and tomorrow we're going to meet at the same link, same time, which is 8 a.m. Pacific time. So see you all tomorrow. Bye.
See you.
Tommy.